Welcome to Lab 4, Part B. Make your own solution of known salinity. To begin this lab section, pause this video and watch Lab 4 Salinity Experiment, Part B. Watch the video now. Welcome back. Let's begin by reviewing the data and the relationship between salinity and conductivity. Notice that when salinity is low, then electrical conductivity is also relatively low. However, when salinity is increased, then electrical conductivity is also increased. This is because there are more conducting dissolved ions in the solution. Thus, as salinity and the number of dissolved ions increases, so does electrical conductivity. Calculating mass-based salinity. Using the data collected in your experiment, we will now calculate the mass-based salinity. For each of your solutions, begin with the mass of salt measured in grams. For example, solution A weighed 2 grams. Next, convert the measured 500 milliliters of water used in your solution and convert it to mass of water in grams using the ratios of 1 cubic centimeter equals 1 milliliter and 1 gram equals 1 cubic centimeter. When we cross-cancel units, 500 milliliters equals 500 grams. Then add together the mass of salt, grams, plus the mass of water in grams. And finally, calculate the mass-based salinity in parts per thousand by dividing the mass of the salt by the total mass of the salt and water and multiplying by 1,000 to convert the units into parts per thousand, the units of salinity. In your lab assignment, complete the mass-based salinity calculations for the 6 solutions in Table 3 and make sure to show all of your work and include the appropriate units. The equation for the best fit line. If you recall, the equation for the best fit line was derived from the calibration curve, where y equals salinity and x equals conductivity. Thus, we can calculate salinity using the equation that we developed in Part A. In the example, we calculated m, or slope, as 0.9. However, remember, this was only an example and your calculated slope may be different. Next, use the measured conductivity for solution A, which was 5.49 millisiemens. Then from the example from Part A, we estimated that B, or the slope intercept, as negative 0.5. But again, remember, this was only an example and your slope intercept may be different. Finally, plug your known variables into your equation for the best fit line from Part A. In this example, the converted measured conductivity for solution A equals 4.4 parts per thousand. And in the last column, add your mass-based salinities from Table 3. In your lab assignment, complete your calculations for each of the 6 solutions in Table 4. Make sure to show all of your work and include appropriate units. Calculating percent difference. Next, we will compare our calculated salinity values from Table 4 to the predicted or mass-based salinity values. To do so, we will calculate the percent difference between the two. The formula for percent difference is calculated salinity minus mass-based salinity divided by the calculated salinity times 100, which for this solution, or for solution A, equals 9%. You will compare the results to whether your percent difference are within 2% and 5%. In this example, our percent difference of 9% is out of range. In your lab assignment, complete your calculations for percent difference in Table 5. Again, make sure to show all of your work. The calibration curve. In this lab experiment, the use of a calibration curve was essential. By using a calibration curve, we were able to determine the salinity in parts per thousand of unknown samples. By plotting a measured conductivity to the curve, we were able to determine salinity. It's now time to complete your lab assignment. For Part B, make your own solution of known salinity. Next, watch video 4, part C, a case study. Again, please address your questions to your lab TA.